Just written homework. Okay. Written homework. You know the drill. Whatever you usually do. It's terrible. Okay. Okay, turn in your written homework. As you're folding it, putting the heading on, is there one in particular from the written that we want to talk about? Which was it? What was that? What was it? That's it? Is all this? This one, should we talk about? Is that the best one to talk about? Okay. So while you're turning that in, I'll do this. So one thing we look for is squares. So we know with the Pythagorean identity and with the half angle formula that involves squares. So that might be an indication that we're going to start by getting out tangent squared. So we're going to break it up into tangent squared times tangent. And why should we do that? Because now tangent squared from the Pythagorean identity, is it 1 minus or secant squared minus? I don't have them memorized. 1 minus secant squared? Secant squared minus 1. I always just derive it every time if I have to. So cosine squared plus sine squared equals 1. So we want to divide by to get tangents and secants. If I divide by cosine squared, watch, cosine squared, cosine squared, cosine squared. So secant squared equals tangent squared plus 1. See that? So do we get this right? So tangent squared is secant squared minus 1. That's right. Yeah, so you can derive those variations on the Pythagorean identity just by dividing all terms by cosine squared, dividing all terms by sine squared. And it gives you those other two forms. Okay, so why did this help? Well, notice that secant squared is the derivative of tangent. That sets up nicely, and then we just have to deal with minus tangent. So I got secant squared u times tangent u minus tangent u. So if secant squared is the derivative of tangent, then that's what we want, right? What can we do? So it's kind of like we have tangent u to the first. And then the derivative of the interior function tangent u is secant squared. So what can I do? Tangent u, what? Squared, half of that, right? Undoing the chain rule. Undoing the chain rule would mean doing the antiderivative of the exterior function here, raising the power to 2, 1/2 of that, and so now the derivative would be exactly this. Tangent u to the first times derivative secant squared. So that's the derivative of that is exactly that. And then for this one, I can change this to sine over cosine, or sine u times cosine u to the minus 1. And we should recognize that. Again, the antiderivative of, the derivative of cosine is essentially sine, right? The derivative of this interior function is essentially that. So I've got, undoing the chain rule again. So it's going to be to the minus 1 means natural log. I just got to work out the plus or minus. So when I take the derivative of that, I'm going to get negative sine, right? Well, there's the negative sign, so I can add that. Done. Okay, so I kind of went fast. Again, so it's always about, so look, it ended up being 2 undoing the chain rule problems, and that's what all these trig integrals really end up being. If it's not something simple, it's always going to be undoing the chain rule. And remember, so and then one more thing about those, whenever you have a form of sine squared just by itself, kx, or cosine squared by itself, that's just so you got to remember, be on the lookout for, it's half angle formula, right? Whenever it's just, but not multiplied, so it's just got to be just sine squared or just cosine squared by itself. You just have to remember that the way you do that is by the half angle formula. And I did an example like that on Wednesday. Okay, questions on that? Do you follow what I did? Another possible thing you could do with a secant squared tangent u is you could group a secant and a tangent together, and you'd be left with a secant. And that works too, because you'd have secant u. This is just a little harder to see, but if you group a secant and a tangent together, now look, you have the derivative here of this. Okay, so you could do what? 1/2 secant u squared. 1/2 secant u squared would also work. When you say, well, this is a different function than that. Well, they're just off by a constant of 1, right? Because 1 plus tangent squared equals secant squared. And so then you just have a different constant. You just have a different constant. Yeah, so this is the other way to do that is what, 1/2 secant squared u. Which are those are off by just a constant of 1, so you just have a different c. Okay, any questions on this example? Does it make sense? Yes, please. No, because we add c, right? So it's a different c that you would add. But this could be any c, right? This could be any c, so call it c1. All right, if you do it this way, you would have ln, you just have a different constant. You get all the same functions, but you have a different constant. See, this is a family of functions, right? Add any value, 5, 4, -6. So this one is the same family of functions, but you'd have to add just a different value to get the exact same one as this. So like if you were to add 2 to this one, you just add, I don't know, 3 or 1. I'm not sure. I'd have to do the math. But for instance, if you add 3 to this function and 2 to this one, you get the exact same function. Does that make sense? Yeah. Other questions? Okay, let's just start one more of these. See if you can get started on it. We don't have to finish the whole thing. Here's one, cosine cubed. Because you still have till 5 p.m. on these. So, can you get, this is cosine cubed 5x times sine to the 9th 5x. Let's just get as far as we need to so we know we could finish it. Give it a try. There's no Wolfram alpha on the test. You got to know what you're doing, okay? Yeah. No, because it was minus already. It was subtracted in the integral. So when you take the derivative of cosine, you get minus. Got it? Yeah. So you should be thinking, I want to set this up for undoing the chain rule. I've got sines and cosines. So that means I want to isolate what? Either a cosine or a sine. Which is the much better choice? If I isolate a sine, then I'm left with sine to the 8th that I got to turn into cosines. No thanks, right? All right. But if I isolate a cosine, this is the trick, fives. If I isolate a cosine, that's going to unlock this thing to get started. Right? If I isolate a cosine, I'm thinking, okay, that's going to be my derivative of my interior function for undoing the chain rule. So that means I want to write the whole rest of the integrand in terms of sines. So I got that's fine. I just got to rewrite that in terms of sine, which is what? 1 minus sine squared. Can you see it from here out? So I have two integrals, right? Sine to the 9th 5x times cosine 5x, and sine to the 11th 5x times cosine 5x, which are both undoing the chain rule. Do you see it? I'm going to distribute. Inside the big brackets. Now I have two integrals, which are both a power of sine times cosine, which we should recognize immediately as each of those would be undoing the chain rule. But then you also have to worry about that 5 in there too. So you just got to make sure you get that, take care of the 5 also. So what do we got there? Sine to the 10th, 5x, and a 1/5. And this one will be? Huh? Yeah, 1/10. Thank you. Yeah, I'm going to have the 1/10 from the power of 10, but I'm going to have the 1/5. Thank you. 1/5 from the coefficient. That's right. Thank you. And then sine to the 12th. We'll need the 1/12 and another 1/5. Questions? So you know the derivatives of all the trig functions. Derivative of sine is cosine. Derivative of cosine is sine. Derivative of tangent is secant squared. Cotangent, negative cosecant squared. Secant is secant tangent. And if you write that down, make sure you know your abbreviations. Minus cosecant, cotangent. So what are we doing? So in these problems, what? We're looking to isolate one of these, right? We isolate one of these to set up for undoing the chain rule. And then we get the whole rest of the integral in its corresponding antiderivative, right? So like this one, I'm isolating cosine, then the whole rest of the integral is in sine, and I got undoing the chain rule. Or if I isolate a secant tangent, then I'm looking to write the whole rest of the integral in terms of secants. And then I can do undoing the chain rule. So we isolate one of these. And get the whole rest of the integral in its corresponding antiderivative. And then we're undoing the chain rule. Does it make sense before we go on to the next topic? Anybody have a question? So again, you have till 5 p.m. to finish up the web work for this stuff. Okay. Can I erase? So new topic here. So let's look at this here. So whenever we come to have to do an antiderivative, we're building a toolbox, and we have to kind of ask questions to identify which tool we're going to use. The first tool we always ask is it undoing the chain rule? Because that's the most common one we want to be on the lookout for. So is it undoing the chain rule? How about this? No. We could think of ln of the bottom, right? Because that whole bottom is to the first power. And then we think of ln of that denominator, but then what? The derivative of that would have to be the numerator, which it's not. Okay? So then I'm doing the product rule. Well, maybe, but it's certainly not one of the common forms, right? I talked about the common forms for undoing the product rule. Most of the time, we're on the lookout for those, so probably not doing the product rule. What about partial fractions? What about partial fractions? Well, no. So here's the deal. So you might think it kind of looks like partial fractions in disguise. Do you see that? Because the denominator is kind of like a quadratic, right? It's kind of like a quadratic. It's just got all these e's. So here's where what we're going to do is we're going to change the variable so that it is truly a partial fractions like we're used to. So this is called change of variables technique. Okay? Or use substitution. Okay? So use substitution. So what we're going to say is, what do we really have here? So it's like e to the x. This is like e to the x squared, right? And 3e to the x. And this is e to the x squared. So we want to set u equal to something that's going to get rid of all these exponentials. So we could say u is just simply e to the x. And if we did that, we'd have what? The numerator would be u squared. And this would be u squared. And this would be 3u. And so it would get rid of all those e's. All right, but we need to know what dx is. Okay, we need to know what dx is. So in order to find dx, what we'll do is we'll say, what's du? Du is, derivative is, e to the x, dx. And this will help us determine what dx is, right? So what's dx? Dx then is du over e to the x. But what's e to the x? It's u. So dx is du over u. See what happened? So I was just solving for dx. It's du over e to the x. But we need dx entirely in terms of u, because we're going to change the variable. We want no more x's, only u's. So then if it's du over e to the x, well, e to the x is just u. So it's du over u. So now we're ready to change the variable on this thing, so it's going to be what? U. It's going to be what? U squared on the top. And that's U squared plus 3U plus 2. And then what's dx? It's not just du. Du over u. Now in this particular example, we have just a power of u in the top and a power of u in the bottom, so then we can simplify those. Okay? But if we had something else in the top that was not just a power of u, then what? This u would gather up with the denominator. You see that? In this case, that u can go away with one of the u's up here. But if it was, say, u squared plus 1, or something like that, well then the u, there's no cancellation. That u's got to join up now with the denominator. But that's, in this case, we got the easier thing. We can just say it's u over u squared plus 3u plus 2. Du. So when you do a change of variables, just all basic algebra rules just still apply. You just got to do the math right. Okay? Don't just think every example is going to be just like this one. You got to do the algebra right. So there could be different variations on these. Okay. So now, what do we got? Is it partial fractions? It is only if what? That has to factor, right? That has to factor. If that doesn't factor, can't do partial fractions. Okay, so, but it does. U plus 1, U plus 2. And then that's the easiest partial fractions problem we could come up with. So I'll go fast, because it's easy. So we're thinking, okay, this has to be A over U plus 1 plus B over U plus 2. Somehow. And then when we add these together, our common denominator will be u plus 1 times u plus 2. And the numerators have to equal, right? So the numerators would be, so to get our common denominator in this first fraction, u plus 2 over u plus 2, right? To get the common denominator in the second fraction, u plus 1 over u plus 1. So that means that a times u plus 2 plus b times u plus 1 all over, I'll just write it out once here. Our original, right? So when I add those two fractions together, now I better get the original thing. Denominators agree, so all we have to do is set the numerators equal, right? So A, so this equals that. Can I expand that in the next step? So AU plus 2A plus BU plus B equals U. And that gives us what? Coefficients of U are A plus B equals 1. 2A plus B equals 0. And so we got a system of equations which gives B equals 2. So I'm not going to, I have the answer, and you can, if you need to work it out, you can work it out later, but that gives B equals 2 and A equals negative 1. So then this integral here is negative 1 over U plus 1 plus 2 over U plus 2 du. And we can, so the point of change of variables is to get something that we can take the antiderivative of. So by changing the variables, we can do this partial fractions technique, and we can get the antiderivative of that, which is easy. Since these are both power 1 in the denominator, we're going to have natural log. Don't forget absolute value. So you don't always have an absolute value on the argument of ln, just when ln is the antiderivative, right? So when you take an antiderivative and get ln, that's when you need that absolute value. Okay, and so now what? But our original problem wasn't in terms of u, it was in terms of x. So once we do that antiderivative with the new variable, then we're ready to rewrite the answer in terms of x. How do we do that? Well, what is u? It's e to the x. So now we're ready to go back and say negative ln e to the x plus 1 plus 2 ln e to the x. Sorry. Yeah, that's right. Is that right? And then we'll put the c on here in the end. So change of variables, in this case, it helped us to kind of take the disguise off the fact that that was really partial fractions. It just was kind of infused with these exponential functions, and so by letting u be the exponential function, it revealed that we did indeed have a real easy partial fractions problem. And then the change in variable is so that we can do, once we get that antiderivative, we'll switch back to our original variable. Questions on this example? Okay. Yeah, please. No. Okay, so I see you're thinking on doing the chain rule. No, because our antiderivative is this step right here. This is our antiderivative right here. And so do you agree this is correct? Yeah, this is correct, right? Because if we took the derivative of that, we'd get exactly this. So now, when you substitute back in, so now the antiderivative is done. There's nothing more to think about in terms of the antiderivative. All you have to do now is just substitute back in. Anywhere there's a u, it's e to the x. Anywhere there's a u, it's e to the x. So if you're still not convinced, then what you need to do is take the derivative of this, and to get the original, that might be a little algebra involved. But if you take the derivative of this, you should get exactly what we started with. So that would mean you would have a couple fractions here. You'd have to get a common denominator, add them together, and you get exactly that. Did that answer it? Yeah. Once you do that antiderivative, you don't have to think about antiderivative anymore. You just substitute back in. Yeah.
To kind of answer a question, make it a little bit easier to see without having to actually solve it. With b and a, technically b equals 2u and a equals negative u. So if you plug that in up top, then undoing the chain rule, it looks more correct. Like that could answer her question. So you have negative e to the x over e to the x plus 1 plus 2 e to the x over e to the x plus 2. So then
Yeah.
that way you kind of see what it's talking about. Like that way you're not so confused. It's harder to do the antiderivative that way, but
I don't know if that helped. Did that help at all? Okay, good. All right. Okay, other questions on this example? Okay, can I erase? So let's try this. So this is also change of variables, but kind of achieves a different result. It doesn't really Okay, first question we always ask. Is it undoing the chain rule as it is? No, okay? So we might think of square root in the denominator, that's like power negative 1/2, but then the numerator would have to be the derivative of that inside part. So no, it's not that. Undoing product, again, it might work, but probably be a little bit ugly, and it's not one of our common forms for undoing product. Remember, undoing product is like x times sine, or x times e to the x, or lots of forms involving ln of x, or inverse trig functions. Those are our main ones for undoing products. So it's probably not that. Partial fractions, well, no, we don't have a factorable denominator, and it's with a square root. So this is not partial fractions. So this may be a candidate for some kind of substitution that might, with some algebra, give us something doable. That's the idea here. That if we can do a substitution, change the variable, then do some algebra, we could get something that we could do. So any ideas? What should we let u equal that might unlock this? So what's really the problem here? Where's the difficulty here? It's really the square root of a sum, right? The square root of a sum is it's kind of an obstacle to doing lots of things. So we could say u is the inside. Okay, so just the inside part, because just the square root of the variable, that's just u to the 1/2. That's easy, right? That's u to a power. That's nice. So let's try u is 1/2 x plus 1. Okay, now we got to look at the integral and we got to say, we got to change this whole thing into u. So what else are we going to need? So that would take care of the denominator. We're going to need to know what x is. And we're going to need to know what dx is in terms of u, and then we can change the whole thing. So how are we going to get what x is? So all we have to do is just solve for x here. Solve for x here. So we'd have u minus 1 is 1/2 x. So what is x? X is 2 times quantity u minus 1, or 2u minus 2. So that takes care of that. Again, we got to write this whole thing in terms of u. So every part of it that has an x, we're going to have to get it in terms of u. So denominator is fine with that first step. We need to know what x is in terms of u. Lastly, we have to know what dx is in terms of u. So here I can just, in this case, I can just differentiate here. I can say dx is what? What is derivative of 2u minus 2? 2 du. So that's all. I'm going to need all this stuff to rewrite this. And why don't you try that step? See if you can now rewrite this integral in terms of u. Go. It's just substitution, just replacing things, right? Replacing things. Okay, you can look up, I wrote it up there so you can check yours. Do you agree? Okay, so do you agree? That's one question. Next question is, did it help? Did it help? What does anyone see? What can we do to move forward here? It's something we could do. So it's something it's a little technique we've seen before. Just have to recognize it. Any ideas? Let me expand the numerator and then see maybe if you see it. Long division would be a little ugly, and it's actually more work than you need to do. So you see I just multiplied up the top, and now what happened? Do you see what you can do now? What's that? No, yeah. We're trying to avoid that, so it's easier. So remember when you have a fraction and you just have a single thing in the denominator, what can you do? Just split it up, right? So we can do that over that minus that over that plus that over that, and those will all be just monomials. They'll be slightly ugly fractions, but it'll be easy. So what's 4u squared over u to the 1/2? 4u to the 3/2, is that right? Minus 12u to the 1/2 plus 9u to the, and that whole thing times 2. So what do we want to do? Do we want to keep the 2 out, or do we want to multiply the 2 in? Doesn't matter. Let's just keep it out. So now easy, right? Just power rule. And just got to make sure we're careful with the factors. So we're going to have u to the 5/2. And we'll need 2/5 times 4. So 8/5. U to the 3/2. We'll need 2/3 times -12. Is that -8? And then u to the 1/2 times 2. So I think we have 18 there. Check my math. Make sure you agree. And I just kept hold on to the 2 outside. How did I do? Did I make a mistake, or is this right? I think 4, that's right. And -12, that's right. And 9. I think I got it. Now what? Yeah, so now I've got to change this back into what? Into x. So anywhere there's a u, I'm going to do what? Put x. Or the u is 1/2 x plus 1, right? So 1/2 x plus 1, 5/2, minus 8. Let's see. If we want, we could factor out another 2 if we wanted to, or we could multiply the 2 in, or we could factor out another 2. This is trivial. This is not the important part. Okay. Did I lose you? Did you follow that? Any questions on that? Yeah. So it's basically just derivative, right? Derivative. It's just, so I'm right here. Derivative of that with respect to u. It's just 2. Yep. Other questions? Okay, what if this was a definite integral? So let's talk about definite integral. So suppose this is, say, from 3 to 6. Okay, so suppose this was from 3 to 6. You actually have 2 options here. So, of course, we could just get this final antiderivative, right? And then we could evaluate it from 3 to 6, just like we always do. But then there's another option to do this, and that would be we could evaluate it in terms of u. We just have to know what the corresponding limits, so that's x equals 3 and x equals 6. We need to know what the corresponding limits in terms of u are, and then we can evaluate the u expression. And so maybe that's more advantageous because it's easier. Okay, so what is u when x is 3? Right, so what is u when x is 3? 1/2 times 3 plus 1. Is that 5/2? And then when x equals 6, what's u? 4? So when x changes from 3 to 6, u changes from 5/2 to 4. So we can evaluate our u antiderivative from 5/2 to 4, and then we get the exact same result. So maybe that's a little bit cleaner. We don't have to write out that step with all the 1/2 x plus 1's in there. Write all that. So maybe we prefer here now easily find out what the corresponding u values are and then evaluate the u antiderivative. You're going to get the same number in either case. But if it's an indefinite integral, you have to do this last step. You have to write your answer in terms of the original variable. Okay? Okay, any questions on that? Okay, and so one place where this u substitution comes in very handy. Can I erase what's up there? There is a table of integrals, common forms. Oh, that's not what I want. There we go. So in every calc textbook, there's a table of integrals. So this may be from a different book, so the numbers may be different than the one in your book, but they're all basically like this. And so you have all these common forms. So there's basic integrals, which you should have memorized, first of all. Then there's trig integrals, okay, some common forms of trig integrals. So just formulas. Here's trig integrals to powers and some reduction formulas. And then the ones that we'll see the most for these tables are integrals involving the sum or difference of squares. All right, so this is x squared minus a squared. These are common forms and often with square roots. All right, so these are common forms and then just formula for what it is, what the antiderivative is, without having to go through some long algebraic technique to get it. It's just telling you the answer in a generic sense, right? So a could be any constant, right? X squared, say x squared minus 4. All right, and so then here's sum of squares. A could be any constant again. X is your variable of integration. Okay, so thinking about these tables, here's an example. Where is it? Okay, so here's an example. 1 over Okay, so immediately you recognize, you see this difference of squares under the square root. So is it undoing the chain rule? No. Is it undoing the product rule? It'd be really ugly if it worked, right? It would be something we want to avoid. Is it partial fractions? No. Is it trig? No. Okay, so with the square root and this difference of squares, we think, okay, maybe a change of variables and maybe applying a table rule. Okay, so in the table, is there something, so we got to look for something in the table that fits this form. So is there one of those particular table integrals that we could get this one to look like? So what I notice is, okay, it's the difference of squares. This is kind of like something squared minus a constant squared. So I want to look in that part of the table. So there's the sum of squares, but those are sum of squares. See that? So yeah, almost. And then I come here, and here's the difference of squares. So is one of these applicable to our problem? Which one? You should be thinking number 70. Number 70, okay? But the problem is, what? We don't have x squared minus a squared. We have 4x squared minus a squared. So we have to do some kind of change of variables so that ours matches this exactly. If we want to use this, this formula, then ours has to match this exactly. Does it make sense? So I'll isolate that here, number 70. All right, so really, let's use u. Okay, so let's use u. So what we want is our u squared to equal what? 4x squared. And that's what's going to govern what u is, right? That's going to govern what u is. So in that case, what is u? Square root of 4x squared, which is 2x. Well, it would be plus or minus 2x, but we don't have to worry about that, okay? Because it's squared, right? So it's squared. So u is 2x. And then we need to know what x squared is, right? What is x squared? U squared over 4. And we're going to need to know what dx is. What's dx? Well, dx is going to be, from this one here, it's going to be 1/2 du. If I solve this for x here, it'd be u over 2, so dx would be 1/2 u over 2. So now by doing that change of variables, I get 1 over u squared over 4 times the square root of, my whole point was to make this 4x squared u squared minus 7. And then what's dx? 1/2 u du, sorry, 1/2 du. And so now this 4 is actually in the numerator, right? So this 1/2 divided by 1/4 is actually just 2. So now does this integral fit exactly the form for 70? Yes, it does now, right? Because I've got my variable squared times square root of my variable squared minus 7. Now the differential of my variable. So now it fits 70 perfectly, and I can just write out the answer, right? So now it's telling me exactly what it is. So I just write this out. It's going to be, so I got a 2, first of all. Square root of u squared minus 7 all over my a squared is 7 times u. And now I can change it back into x. What's u and what's u squared? And what is u? 2x. Let's see. Yes, please. Yeah. Okay. So it actually, coming out of the integral, it actually be 1/2, right? Yeah, so you divide that whole thing by 4. Yeah, so you come out as a 2, and then you wouldn't have to change the variables, and you can just use it. Yeah, that's a good point. But I wanted to show that oftentimes when you use these tables, you're going to set up the ability to use a table formula by first changing variables. You'll see that a lot. So yes, that's possible in this case if you want to do that. Okay,